So welcome to the halfway point. Thanks for sticking around. Today we're going to talk about using particles from space as we have been, but now cosmic ray air showers and how they may help us understand the birth of lightning. Very fancy, yeah. So what we've talked about in a little overview from the past couple lectures, a little overview of the past couple lectures. In lecture 1 and 2 and 3, we talked about changing our lens. We talked about the electromagnetic spectrum, right, where we have radio waves up to X-rays, visible light that your eyeball measures with, and then gamma rays, the highest energy kinds of electromagnetic radiation. We also had muons, which we learned and talked about a couple lectures ago, go through a ton of material, right, and allow us to probe and X-ray hundreds of meters of rock, including in volcanoes, and I'll give you a little reminder of that, right? And so the muons that we talked about a couple lectures ago were existing because of a bunch of cosmic ray interactions, and we said, well, these muons penetrate, they probe very deeply, they interact, they very weakly interact through a bunch of material, hundreds of meters of rock, and we can put detectors at certain locations to back out the density profile of the rock through volcanoes, for example. So if you're interested in that, you can go check out lecture 2. And there's a bunch of projects like the Mu-Ray project that does this kind of muography. We also talked last week about even more penetrating particles. We said that muons are charged particles, and if we got rid of that charge, we get a very weakly interacting particle, right? And you have something that's so weakly interacting called neutrinos that actually go through all of the material, all of the concrete. They can even go through the entire Earth. And this is kilometers of rock. And this is actually why it's called the weak force, right? It's because these particles basically don't interact at all. You have to have so much material in the way, right? And you needed large detectors to measure these neutrinos, okay? That was last week. So if you're interested in that one, you couldn't attend, also online, you can watch that one. But basically we said, you can use these neutrinos that are always coming from different cosmic ray interactions in the air with huge detectors like IceCube to even probe the density profile of the entire Earth. And this has been done, this is called neutrino tomography. And it's an ongoing research project that a lot of people are very interested in. So in lecture 1, I started with trying to convince you all that basically what we're trying to do is put on different lenses to understand different things about the way the world works. We could see through opaque objects with X-rays. Right? And so we took the example of the Milky Way that you look at with the night sky with your actual eyes, right, with optical lenses. And you can use X-rays instead to get an image of the center of the Milky Way that you can't with optical light. And this showed us that the center of the Milky Way is so bright, it's glowing in X-rays because it's gas that is millions of degrees hot. Right? We also said the discovery of X-rays allowed us to see through that opaque objects just like that X-ray lens of the Milky Way center. Right? And this is the example I kept referring back to about Röntgen's hand, right? You can see through opaque objects, one way of looking at your lens. So we have established that you can use cosmic ray muons as a lens to see through a lot of material, and neutrinos as a lens to look through even more material. And we get these cosmic ray muons, and we get these cosmic ray neutrinos because of cosmic ray air showers. Oh, there's a huge bug at the front of the... Interesting. It's not a muon, don't worry. Oh. Sorry, it freaked me out for a second. I'll stay on this side. I'm not scared of bugs, I just don't want to step on them. So what we've established is that you get these cosmic ray muons and neutrinos, right, because they propagate from somewhere across the universe. They come from and are accelerated at extreme energies from across the universe, and they make it to Earth and they interact in the atmosphere. And when they interact in the atmosphere, you get showers of particles. That extreme energy of one particle turns into a bunch of other particles at lower energy, right? And those particles are produced because they break apart the nucleus of different air molecules in the atmosphere. And this allowed us to also say why it makes so much sense that we had to go higher in altitude with balloons to even understand that these particles are coming from space in the first place. Right? This was what we talked about in lecture 1, where there was Victor Hess and others ascending on balloons to measure cosmic radiation and see that it's increasing with altitude. You could get higher energy particles as you go higher into space. And so we have ballooning projects that I work on that go all the way basically up into space to measure those particles directly. And we also had studies of particles on the ground that are the remnants of these ultra-high energy particles that collide in the atmosphere, right? And so coming back to those ground detectors that we talked about cloud chambers, right? And then in the 1930s, the cloud chamber was improved. We had coincidence measurements, where you have these cosmic ray interactions producing ionization trails. And novel experiments at the time were invented that used Geiger-Müller counters to make a coincidence measurement as the particle started on one end of the chamber, went through the chamber to another counter on the other end, to immediately take a photo autonomously, right, to capture that track. And this is what the kind of development was, detector-wise, to allow us to study cosmic ray muons and positrons, etc., right? So the cosmic rays and the novel detector developments basically birthed particle physics, and we reviewed that in lecture 1. But the story around the same time branches. It branches because the cloud chamber showed us that there were actually showers of electrons. That's why I said branch, right? Because it's a bunch of particles branching here at the top. And we also understood that muons go through a lot of material that don't create those showers. And so two theorists at the time, I spelled his name wrong. That's really embarrassing. Baba and Heitler made a new theory of cascades, where basically electrons in material undergo what's called Bremsstrahlung. And so you have an electron coming in with enough speed that it emits a gamma ray by interacting with the atom, and that gamma ray goes on to interact and pair produce an electron-positron pair, right? And so in a very short time window, we developed an understanding of these kinds of processes, what will eventually be called cascades, right? So remember, the muon was only discovered right here in 1936 or 7, right? All of this has to do with the images taken with cloud chambers, such as Carl Anderson's here, of these electron showers, right? And so the way this cascade theory works is that you have a high-energy particle coming in and producing a gamma ray, but that particle keeps going, like the previous animation showed. And as that particle kept going, it also produced more because it still had some energy. And at every single one of these stages, a new generation of particles is created with lower energy but higher number of them, right, to conserve energy, right? And so some of the actual photos from 1937 of these cloud chamber measurements show, they said, we're not even going to bother counting this, guys, but we know there's at least 300 charged particle tracks in this one image, right? Showers were a thing that were trying to be studied, trying to be explained. And one of the leading theories at the time that still works is Baba and Heitler's theory of electromagnetic cascades. And so the way this works is you have a high-energy photon, for example, a gamma ray, coming in and undergoing pair production, and those two particles have half the energy of the original, basically, right? And the electrons and positrons then emit gamma rays themselves through this Bremsstrahlung process, this breaking radiation, but they also keep traveling, and now they have half the energy. This gamma ray has half the energy, but now you have twice, and you keep doing this process, right? So in materials, these singular high-energy particle transforms into many through a cascade. So along comes 1938, Auger says, I have a wonderful idea. I'm going to do your coincidence method, but I'm going to put those coincidence method Geiger-Müller counters over 300 meters apart, right? So that's 1,000 feet apart. And as he puts those at different distances, he discovers that some of those particles, some of those counters, still go off coincidentally, right? And over large distances like this, he did a really proper analysis, and he said, there was one particle that must have created both of these. It can't be the same particle coming through both. It has to be a one particle producing multiple that can establish this kind of coincidence experimental result. He even did an analysis that showed how often the accidental rate would occur from just having those counters there from all the other particles they already knew about. And you can see the dashed line showing what that accidental rate should be, but then the obvious measurement here at 300 meters, ridiculously higher in number, right? And so this established that showers are happening, cosmic rays are coming, or some particle is coming in with enough energy to fire my detectors that are placed 1,000 feet apart. And so Auger said, I'm going to call this some French way of saying it that I don't know, the Grandes Gerbes, which is the great shower, right? And so what he decided to do was basically repeat the same experiment but at a higher altitude. And so if you want some of the details, the instruments were large at the time. They were 200 square centimeters, and he went and put them a few kilometers in altitude up in the Alps, actually. And he was able to get an estimate for the number of particles, and with his estimate of his counters going off in different configurations, he was able to say there must be 1 million particles originating from this singular one, right? And one of the consequences that he explains in his paper is that these cosmic rays must be up to 10 to the 15 electron volts. And he said it's actually impossible to imagine a single process able to give a particle such an energy. So at the time, the scale was completely different. This is a peta-electron volt of energy that no one had ever heard of. All right? What we discussed last week with neutrinos was that Ice Cube, the detector, actually measures neutrinos with this much energy, but that's a very modern result. So we've sort of seen peta-electron volts last week. But before this, around the same time before this, the expectation of those cosmic ray particles was that they were 10 giga-electron volts of energy. So these new showers were particles that Auger said are 100,000 times more energetic than the ones we previously knew about. But it was unknown what kind of primary particle, we're going to use the term primary to describe the particle that comes in, primary particle it was. They didn't know if it was a proton or a gamma ray or what. So just to really drive the point home, it's actually kind of a fun exercise to try to figure out how to explain what that much energy means in a single ball of one particle. So the way that I've started to think is probably a pretty good way of explaining it is, think of shooting a ball of light, just press your switch on a laser and shooting it into space, and seeing how far it goes after a year, right? It's a laser, it's traveling at light speed, so in a year it goes a light year, right? That's your light particle. It's traveling at the speed of light, the photon. If you took just around that same time the highest energy cosmic rays they knew about, giga-electron volt scale, for example, 2 giga-electron volts in a proton, it goes 86% the speed of light. So from the standpoint of the Earth, if you had fired that proton at the same time, it would go 86% of a light year, right, from the standpoint of someone on Earth. So this scale, if you go up by a factor of 1,000 almost, right, in energy to a tera-electron volt, that particle basically goes now a full light year. It's actually about 4,000 kilometers shorter than a full light year as it's traveling from the standpoint of someone on Earth, right? This is actually only, on the scale of a whole light year, this is only a billionth of a light year. So it's traveling pretty fast, right, after a whole year. So if you take Auger's new particle of even more energy finally that he measured, it's only 4 meters behind the photon. After a year of traveling, it's insane how much energy at the time. So to appreciate the energy scale of that, at the time it was groundbreaking. And we're going to see that a lot of the stuff about cosmic ray air showers is sort of startling in a way that, a lot of the community doesn't want to accept. One of those people is Bruno Rossi. So he actually played a huge role in the 1930s with different cosmic ray experiments, including this coincidence method. So here he is talking to Robert Millikan, and you guessed it, Arthur Compton. So he was invited, so I said his name, 4th lecture in a row, if anyone was keeping track and placing bets. So those of you who said 3, you don't win. So 1938 is when he was invited from Italy because of all of the problems that were happening with fascism in Italy. In 1938, Compton invited him to work with him here at the University of Chicago. And, he developed a good relationship with Fermi and many other scientists in this area. And I found one excerpt that I thought very interesting, which is when he thought back in an interview, when he thought back about all of those experiments in the 30s that he did looking into cosmic ray particles and air showers, he said they were simple experiments, but they were so startling, the results were so startling that he had trouble getting them published. Right? And so that is matching what what we're seeing with other things in this area as well of cosmic ray air showers at first. So fast forwarding now to these showers exist, these cosmic rays exist with this extreme energy, right? There were a host of particles discovered. There were pions that were discovered, and there were kaons discovered, and these are actually stranger particles. The kaons are strange, but that's a side joke for those of you who know about kaons. We're not going to talk about those in particular, but what I do want to get across to you here is that a very high energy cosmic ray proton interaction produces a shower of particles. So if your cosmic ray comes in, a proton comes in, it, just like the electromagnetic cascade, produces a bunch of other particles in the air, and those particles produce other particles, and this shower generation develops, right? Where each generation has lower energy. And the kinds of particles we can measure, or we talk about with these cosmic ray showers, is electrons, positrons, muons, even neutrinos, right? You have all these different kinds of particles that can be measured in these showers. And this is actually how pions were discovered in the first place, as cosmic ray interactions in the air. But we're going to ignore neutrinos this lecture since we gave them a whole lecture last week. So coming back to Rossi's research, he decided in the 50s to develop a new program of a big ground-based detector array. All right, and this was deployed at Oak Ridge Observatory. So him and his team went to work developing scintillators, and they said, well, let's place these 11 different detectors spread out kind of like Auger did, but at a much bigger scale. And they had this one problem, which was the scintillators that they did develop were liquid. The material was liquid. So they actually, when they started deploying them at Oak Ridge, well, what is now called Oak Ridge Observatory near Harvard, what they did was they used liquid scintillator, which meant that some of their detectors were catching fire in the field a lot. So they had to say, well, let's go and stop this process. Let's develop plastic scintillators. And so that's actually what led to modern day cosmic ray muon counters and things like, and cosmic ray muon detectors and things like that, was the plastic scintillator development by Bruno Rossi's group. And so the way this works is a cosmic ray particle, muon, electron, interacts in the scintillator, produces light, and that light is measured by photomultiplier tubes. And so they were able to say, well, actually, cosmic rays are even higher energy than Auger had said. They're 10 times and even up to 1,000 times the energy. So Rossi's group measured cosmic rays at 1,000 times a petaelectron volt. And so Rossi reflected on this, saying there seemed to be no end to the kind of energetic particles that nature can produce. And the ability to understand this energy range and measure it was because he could measure the density of the particles, right? Instead of just counting the number of hits, he could actually measure them over a range of different distances and count their profile of the shower, right? And so, for example, a 100 tera electron volt proton, so this is a little lower energy than this, the density of those particles in a meter squared for different photons and electrons and muons extends out to hundreds of meters away from where the cosmic ray interacts. So the cosmic ray comes in at one axis, one point really, but hundreds of meters away, the particles spread out, right, from their interactions. And so this way of developing a measurement of the density profile of the showers allowed them to more accurately measure and understand those cosmic ray particles that were coming in, those primaries. One of the main players at the time as well, in Rossi's group actually, was John Lindsley. So this is nearly 30 years after Auger's measurement. Lindsley said, I'm going to go to Utah to what was called Volcano Ranch and basically scale up the Oak Ridge Observatory one that Rossi's group had made. So here's a picture of him at the Volcano Ranch setting up his detectors, right? This is 19 detectors now, so maybe double the number of scintillators. But the spacing was much larger, 850 meter spacing. To get that distance, just so everyone knows, you have to walk from here to the Midway skating rink. That's about the distance you have to walk. That's how far away one of his other detectors would be from this one, right? And so the actual square area that would cover is close to 8 kilometers squared, right? And so this is him saying, I want to measure these particles, but I know they have these showers at large areas on the ground, right? Because they have so much energy, they produce so many particles that spread out. I need to deploy something like this, right? And he was actually able to measure cosmic rays with energies up to 10 to the 20 electron volts. And so apparently Rossi, at the time this measurement was announced, was vacationing in Italy, and he cabled this statement saying, this exceedingly large shower found by Lindsley confirmed extragalactic acceleration mechanism for cosmic rays. So this meant that we didn't even believe, back then when this was discovered, and we still don't, anything in the Milky Way can produce particles of this energy, right? We think that there's no way something in the Milky Way can do this appreciably where those particles make it to Earth. And so just to put that in perspective again, right, the photon goes in 1 year a light year, and the proton at 2 GeV goes 86% of a light year. And the proton at 1 PeV for a year goes 4 meters behind the light, right? This particle that was measured at Volcano Ranch in 1961 is only 40 nanometers behind. That's how fast, that's how close to the speed of light it's going, right? And so that's like saying, after they're racing for a whole year, the photon says, haha, I caught you by the size of a DNA molecule, basically, right? It says, darn, so close. I mean, he was never going to catch him anyway. You can't travel faster than light in vacuum, but whatever. So, in summary, cosmic ray air showers, right? The primary cosmic ray comes in, interacts, produces a large number of particles from a cascade, and we've deployed large surface arrays to detect those particles on the ground, right? And we understand the actual particle physics that entails here. We have pions that are created, we have photons that are created, we have electrons and positron pairs that are created, right? And in each generation, as you go deeper and deeper into a shower, each particle has less energy, but there's more of them, right? One of the other arrays at the time that was, I should mention because I'm here at the University of Chicago, was Professor Jim Cronin's group developed the Chicago air shower array. So Cronin was famous for also winning the Nobel Prize in 1980 for his discovery 20 years ago of CP violation in those strange particle kaons. So if you're interested in that, you should Google it later. But basically he said, we're going to take the Volcano Ranch idea and scale it up 100 times, right? We're going to make almost 1,100 detectors spread out over a much bigger area. And we're also going to couple it with an underground array of muon detectors, right? So the scintillators are on the surface, and now we're going to, underneath, we're going to put a bunch of muon detectors, right? And so the kind of description here was the Michigan muon array with CASA was CASA Mia. So if you want to Google that later too, this is the kind of profile you get where these detectors, right, are spread out over a much larger area. But the point of the science here was actually to try to study gamma ray showers and cosmic ray proton showers separately. And so this was in a sort of a lower energy range, but much more precise because those detectors were so much larger in number, right? And so I don't want to summarize a whole significant field of science here in cosmic ray showers, but I kind of have to. Casamia did wonderful work in the 80s and 90s to help us learn about gamma rays and cosmic ray showers. And the difference here is the muons. In cosmic ray proton showers, you have the pions interact, hadronic is what it's called. You have pion interactions which produce muons. But the photon gamma ray showers, you really don't have muons. You only have electron positrons and more gamma rays. So the red guys are the photons, electrons, and positrons on the right. That's a gamma ray coming in. And then a proton coming in produces showers on the left, right? With many different colors because of many different kinds of particles. So if you could put on your particle lens and watch a shower happen in air, this is an artist rendering that I stole from NASA that sort of shows you what you should be thinking about, right? So I thought that was pretty cool to show because it's just amazing to think of how many particles it is. I don't think there's millions of particles there in the shower, by the way. It's kind of summarized. But anyway, it gets the point across. So much energy, so many particles. How they spread out is a known, understood thing. How we can use particle physics interactions to understand that propagation and process in the atmosphere is an understood thing. And so many of people have said this is basically a particle zoo, and I'd like to extend that and say it's a detector zoo as well, right? Because you actually get other kinds of emission from those particles. You don't just detect those particles themselves in the shower, you can actually detect traces of them in the atmosphere. Those particles in the atmosphere, such as the muons and electrons, have ionized the air as they travel through the atmosphere. They ionize the air and actually emit UV, so it basically makes the air glow like a fluorescent color. And so we have fluorescent telescopes to measure that. We also talked last week about Cherenkov light, and a lot of the particles in the air here are also traveling faster than light does in air, because light slows down in air. And so this actually means that you can construct a zoo of detectors to measure these cosmic ray showers, right? Because there's a zoo of particles. And the kinds of interactions that happen allow us to measure things like the Cherenkov emission, the fluorescent emission. We even have radio wave measurements of those showers. And then you have scintillation counters that I've been talking about a lot, and even underground muon detectors, right? And so the point is to really understand how the universe is accelerating particles to these energies, right? We're trying to do a very good job of both measuring those showers and characterizing them in many of these different ways. But the other aspect of this is that what it really means is as you go to higher altitudes, you have more particles at high energy, but you have less total number of particles. As you go to lower altitudes, you have more total particles, but less particles at high energy, right? So you're basically losing energy through the atmosphere in the form of creating new particles. And I don't want you to walk out of here thinking that, just walking around, you're going to all of a sudden measure a bunch of particles going through you, because the flux of these really extremely high energy particles is actually quite not so frequent. So we talk about flux, meaning through a given area, you have some rays or particles going through a certain area in a given second. That's what the idea of a flux. So cosmic rays at higher energy are actually rare and less frequent. What's plotted here on the bottom right is the flux of those high energy cosmic rays versus the energy. And so what we talked about was maybe Auger measuring particles here, maybe Volcano Ranch measurement with John Lindsley was here. But the kinds of scales of detectors show you that you need even bigger detectors because the flux falls off with energy. Higher energy, less number of particles. So if you want to think about it this way, if you want to say, okay, put me in space because these high energy particles don't make it to the surface of the Earth, and I just hold out my hand, how long would you have to wait before you caught one of these particles? 6 billion years. But if you want to be 99% confident, 30 billion years. So if I was to go in space for 6 billion years, I wouldn't be just doing that. Anyway, particles are accelerated somewhere in the universe to these extreme energies. And I'll revisit that in the last lecture of the series, right? These extreme energies, these ultra-high energy cosmic rays, and even some neutrinos. So the data, different experiments over the 50 years, 60 years of these kinds of surface arrays has shown us this flux, and they all seem to agree pretty well. Right? There's some things that the community is trying to work out, but overall, pretty good agreement. There's a bunch of high-energy particles. This is the picture we've painted, right? And we have direct measurements where we've actually been able to measure those particles in our detectors above the atmosphere, right, before they've interacted. And then at very high energies, you can never do that, right? Because the flux, they're much less frequent, right? They're so rare. So indirect, just like neutrinos last week, we have indirect measurements of cosmic rays at very high energies, right? And these are the air showers that I've been talking about. So there's one other experiment that I work on that I'll talk about in a couple weeks. Where'd my pointer go? I think the bug ate my battery. Hold on one second. Oh, there it is. So one other experiment that I work on is called Helix, and I'll talk about that in a couple weeks. That's a direct cosmic ray measurement, which means it's measuring cosmic rays at lower energy. It's going into space to do so. So when I did the calculation this morning, just to brag a little bit, when I did the calculation this morning, if I wanted Helix to directly measure particles out here, it would have to be up in the air for 1 million years. And the flight that we had a couple years ago now was only 6 days long, so that puts into perspective for you too. So remember Jim Cronin, who developed the Casamia cosmic ray array, right? Worked with Alan Watson, actually, who gave, I think, the Simpson lecture here maybe 10 years ago now. They came together and they said, let's build an even bigger, novel, new array called, and name it after Auger, Pierre Auger Observatory. And so this was deployed in Argentina at very high altitude with over 1,600 different surface detectors and a host of other different kinds of detectors, including radio nowadays. So it took them actually a long time to get this going because of how many detectors it was, to put them all together to start measuring these cosmic rays. The 100th detector was actually installed in 2003. Part of the group that did that was my advisor, Jim Beatty at Ohio State. But by 2008, all the surface detectors were completed. And so the square area that we're talking about with this kind of setup for all these different detectors for Auger is 3,000 square kilometers. So that's, if you look at UChicago, it's about a square kilometer. So that's 3,000 UChicagos. That's how big of an area to measure cosmic rays Pierre Auger, the Auger Observatory has constructed, right? And a picture on the left here shows you the distribution of all those different detectors. And on the right is a small measurement of an air shower that shows which part of the detectors went off simultaneously, showing that there was an actual cosmic ray air shower measured, right? So you need this large area because you want to measure more of those particles, and the flux of them is so small. So the question that you should be thinking about now, hopefully, is how do cosmic rays get produced? How is the universe capable of producing particles of such high energy? And the answer is we're not sure yet. We have ideas. We have some ideas such as active galactic nuclei, which have just extreme different kinds of fields and material falling into black holes producing and accelerating particles to extremely high energies, right? Stuff like this. We also have different things like supernova remnants maybe, but at a different scale than that's happening in the Milky Way. The thing we do know is that charged particles can be accelerated by strong fields. Okay? And we kind of know this from the other things I've talked about in these lecture series, where if you have a really high voltage applied, you can get charged particles to go very fast. You can get electrons. I talked about Crookes tubes a couple lectures ago, and things like that with cathode rays and beta rays. You can get particles to relativistic speeds, at least electrons, with voltage, with electric fields. And so what I talked about in lecture 1 was with a different kind of lens, you can observe different processes, and the radio measurements of the center of the Milky Way allowed us to see that particles like electrons are interacting with some of those fields, like magnetic fields, emitting synchrotron radiation. And so this revealed both hidden structure and showed us what kind of processes were going on by putting on a different lens, right? We said that there's different kinds of emission. The X-ray emission from the center of the Milky Way was hot gas, but the radio measurements was from these processes. So I said that there's things like incandescent light bulbs that are glowing, that are emitting light because they're hot, and there's things like neon signs that are emitting light because of the ionization of the gas, right? And so one of those things that I sort of mentioned in lecture 1 was corona, which was the breakdown of the air because of a strong electric field. So, and one of the things that I did here was trying to use a high voltage supply that I'll come back to maybe in even the next slide, is try to test it out in vacuum, and I got this nice beautiful corona showing that the voltage, even with residual air in the vacuum chamber, was enough to produce corona, right? And so one of the other things I got to do is build a high voltage tracker that I'll talk about in a couple weeks. So the high voltage tracker here, this is really dangerous, high voltage tracker here, a bunch of wires and different circuit boards at really high voltage, actually gave me electric breakdown in the air. And so one of the videos I took shows you that electric breakdown on the right, the arcing, right? But to put that in perspective, the idea, the number you have to have in your head for an electric field to give you an arc like this is 3,000 kilovolts per meter. Okay? So that's actually a very large, that's the number in air. If you go to a different gas, if you go to vacuum, you don't need as strong of an electric field. But in air, to get these kinds of arcs, that's what you need. It also shows you that experimentalists get to play with a lot of cool toys like these. So if you're interested in experiments, this is the kind of cool stuff you get. So coming back to that electric breakdown, there's this law called Paschen's law, which is if you have a strong enough electric field, you actually get the electrons in your atoms to jump through the air across a gap that they normally wouldn't, right? And that's why right now there's not a bunch of arcs going off, but if we were inside of a very strong electric field, we could get arcs of electrons. And so the law actually, this Paschen's law actually shows you that it depends on the pressure of the gas and the distance between the two objects with the voltage across them, right? And so if you want to think about it, right, the air is an insulator, but the field is just so strong that it doesn't care, right? It now becomes conducting. And so in air at sea level, we have mostly nitrogen from this plot, this purple magenta line, and that gives us about 30,000 volts actually. So up here, over here at the air pressure, we get about 30,000 volts for a 1 centimeter gap at air pressure, right? And that corresponds to that electric field of 3,000 kilovolts per meter that I showed on the previous slide. Kilovolts per meter is the unit that we'll be using to talk about electric fields and lightning. So is lightning just a much bigger one of these arcs, right? And the answer is the electric field at the altitude of where a thunderstorm is needs to be about 1,500 kilovolts per meter, right? In order for that kind of arc to happen. Because at altitude, it might be lower pressure, but that lower pressure still means the electric field has to be this strong. So that's about half of the electric field that needs to exist here at the surface, right? And so one of the images I found was that how does lightning form? Well, you have different charges accumulating at the top and bottom, positive at the top, negative at the bottom, mostly because of a process that allows, ice crystals to go up and down, which has charge exchange. This means that thunderstorms have an electric field, right? And the thing is, even with that kind of electric field, it doesn't reach the breakdown limit. The way you get an electric arc, a lightning bolt, does not match what a lot of people used to think about the electric field breakdown, the electric field in a thunderstorm being so strong that it just breaks down the air, kind of like an arc that I showed you, right? And there's actually, when I was doing a little bit of research into what kind of cool image should I show, this was a nice one. There's actually many different kinds of lightning, and this is a whole different field that, I'm not an expert in, but I don't want to summarize too much about this entire community's research, but it sounds like a really awesome field, and you'll see why here in the next slide. Because if we go all the way back to the cloud chamber inventor, the cloud chamber was the device that we trapped those cosmic rays in. Wilson was actually the guy who invented it. He also contributed significantly to the study of lightning. He even tried to measure the corona discharge. Here's another picture of what corona looks like. This isn't my research, though, right? He said, well, I'm going to go out in the storm and have people that I know and myself hold very sharp metal objects and very curved metal objects in the air, walking around in a thunderstorm. And they even walked up high altitudes to do this, right? And on top of buildings to try to measure the amount of the electric field in the storm, right? They were able to prove that charge leaks from the ground to the air, saying, yes, there must be a strong electric field, right? There must be a strong electric field for the thunderstorms. Nowadays, or actually the transition was that nowadays we have balloons and rockets that actually fly into the thunderstorms to try to measure these different fields. And I found it really interesting that Kurt Vonnegut's brother, he's a famous author, obviously, for Slaughterhouse-Five, but his brother Bernard was one of these people that launches balloons into thunderstorms. In the 1950s, he did this a lot. Nowadays, we actually launch rockets into thunderstorms, and we leave wires hanging off of those rockets attached to the ground to create our own lightning, right? With the goal to understand the electric field of the thunderstorm. And so what you'll see on the right, I don't want you to miss it, but what you see on the right here is that we can trigger our own lightning. Let me see if I can play it again, because it's very subtle in the video, but you can totally make it out. If you watch the bottom here very closely, as soon as I click play, you'll see the bright light of the rocket go up first, and then the wire disintegrating because of the lightning bolt that's created. Oh no. Teaser. No. Let's see if I do it again. Yep, there it is. So, then I can, you can look at the research for this stuff online and find that it's actually really fascinating. A wonderful community of researchers and, experimentalists get to do the coolest things. They get to play with the coolest toys. So, does lightning actually reach the electric field needed to cause a lightning bolt breaking down of the air, right? And the answer from all of this research from the 50s and onward is it's complicated, but probably not. We've never seen an electric field measurement, even though we've flown these instruments in the storms, that actually gives us the electric field breakdown we know is needed to make lightning trigger and go through the air gap of kilometers to the ground. It doesn't match. The kind of electric field that we have measured is 50 kilovolts per meter up to maybe 150 kilovolts per meter. So that's a factor of 10 less, right, than what's needed. Even at these high altitudes, you still need at least 1,500 kilovolts per meter. So, and the measurements are actually pretty robust. The community is very convinced this is not what's happening. So a lot of different avenues of research have been explored over the past 20 to 30 years. All right? Somehow lightning strikes happen even though they don't break down. They don't reach the fields needed. So one of the leading theories is called the relativistic runaway electron avalanche, RREA. So it got a ring to it, doesn't it? All right. Electric fields below the breakdown level. What happens is, even though it's not at the breakdown level, even though it can't just make an arc, if there were free electrons, it matters if those electrons, if there were free electrons, it matters if those electrons are already moving really fast or not. Right? And so this is called the braking radiation, the braking force. If electrons were moving pretty fast, they wouldn't be able to sustain lightning because they would encounter a friction type process and slow down. But as soon as they reach basically relativistic speeds in the electric fields of the lightning that we have measured, they actually run away. They're accelerated. They get the energy of the electric field that the lightning has, or that the thunderstorm has. They get the electric field that the thunderstorm has, and those electrons, being already so fast, can sustain over a very long distance that speed, right? And they even create more electrons when they do this, right? So if they have sufficient energy, if they're across this gap, this barrier, they can now both keep going in the thunderstorm because they're accelerated by that field more than the field is dragging them, or more than the thunderstorm is dragging them back, and they contribute to the process by freeing more electrons. And so Professor Dwyer at the Florida Institute of Technology, he's actually one of the people that launched the rockets that I showed you into the thing. His advisor was actually Dietrich Müller here at University of Chicago, who was a famous cosmic ray scientist who passed away, 4 or 5 years ago or so. So he was a student here. He got his PhD in cosmic rays and then transitioned into this lightning research. But Dwyer also and others cite this kind of process as attributing it to Wilson's idea in 1925. So over 100 years ago, Wilson had already kind of thought about the fact that you can get electric fields in thunderstorms that might be capable of producing runaway electron avalanches, right? And so one of Dwyer's papers shows you sort of the generation of upward lightning here, actually, right? For electrons at 1 atmosphere of pressure, where an electron has enough energy, and the simulation shows he can get many more electrons at that extreme energy inside of the thundercloud. But if he doesn't have that relativistic electron, this doesn't happen, right? So one of the other aspects of this research, of this theory, is that if this is happening, you should also be getting gamma rays and X-rays. And that was one of the main motivators to launch the wires and rockets into the clouds to trigger the lightning to measure those gamma rays and X-rays directly, right? And so the kind of picture that developed here was, if we went and measured gamma rays and X-rays, the black here are electrons, the red is positrons, and the blue is a bunch of gamma ray photons. The simulation says that we should be able to see a bunch of gamma rays emitted because all these electrons are slowing down in the thunderstorm from bremsstrahlung that I talked about many slides ago now, right? But both the electrons and the positrons should emit these gamma rays. And in fact, the gamma rays from one area can actually travel to the cloud and initiate more electrons and positrons at relativistic speeds. So you can get across the cloud many regions connected once you have some relativistic electrons. And the gamma rays should come out of this too. You should be able to look at thunderstorms and see gamma rays. So one of the telescopes that I mentioned was the Fermi Gamma Ray Telescope, right? And at the time, this is sort of understood in the late 90s as maybe a thing that's happening. So this video sort of illustrates to you what Fermi sees. This is what Fermi sees if you just want to look at gamma rays. But basically, those gamma rays are coming from different regions of thunderstorms, right? So there's a gamma ray signature associated with thunderstorm clouds. Now, we haven't even reached lightning yet. We're just talking about thunderstorms, right? Right? And a lot of scientists at the time actually said the gamma rays from Earth were not really possible. So these kinds of detections were sort of novel. And they named them terrestrial gamma ray flashes. So let's see if I think I have, yeah, another video here shows you above a thunderstorm, basically, gamma rays coming up and being measured by gamma ray satellites that were actually designed and utilized to measure gamma rays across the universe. When you look back here on Earth, it looked like thunderstorms are emitting gamma rays, which is what's happening. And this was actually first discovered by the Compton Gamma Ray Observatory, so I mentioned his name twice in this lecture. In order to have a satellite named after you, must have a lecture series first. So the idea that lightning and thunderstorms can accelerate electrons to very high energy is now, there's a link, right? There's a link because we know gamma rays are high energy signatures. So the thunderstorms are producing particles of extremely high energy, or the thunderstorms already have them, right? There's now a link between those two things. And so we have to go investigate, right? And one of the things they said is we have to get closer to the thunderstorms. There's just an idea here of like, let's just launch things into thunderstorms, which I love, right? And so one of the cool pictures you have, which is an ongoing process, is flying a modified U-2 spy plane above different kinds of thunderstorms with gamma ray and X-ray detectors on board to try to get closer and measure the gamma ray flashes. Because in space, you're so far away, you can't see all the gamma rays all the time, right? You might see some thunderstorms, but you won't see the gamma rays because they don't make it to your detector. If you get closer, you can figure this out, right? And so this is a big ongoing new study that sounds really interesting, so stay tuned if you're interested in that, right? Another experiment that I want to mention related to thunderstorms is GRAPES 3, which is the gamma ray astronomy at PeV energies. So basically, they designed their instrument in India to measure cosmic ray air showers, basically measuring cosmic ray muons and trying to come up with a measurement for the cosmic rays that created those muons, right? And so the idea, a picture actually of GRAPES 3 is here with a gamma ray sort of drawn on top, or a cosmic ray drawn on top, initiating a shower, and all of these telescopes measuring the muons. So they actually measure the cosmic ray muon flux so well, and did this during a thunderstorm, and were able to say that during a thunderstorm, we can calculate how many less muons we received, and that allowed us to make a measurement of the electric field inside the thunderstorm. But this was higher than what had been previously measured with instruments that went inside of thunderstorms. So it's sort of a thing that the community's trying to figure out. Is it really 650 kilovolts per meter? Is it more like 200, which our instruments say? And it might be the case that because these muons are going through the entire thunderstorm, whereas measurements of instruments locally inside a thunderstorm are only of certain regions, that some regions of thunderstorms reach much higher electric fields, right? But this is still not enough to make the breakdown of lightning, or the breakdown of air initiating lightning. So what actually seeds the lightning? And so you know this is the astroparticle lens. Now I can't say this with certainty, right? This is still an ongoing field of research, but as early as Wilson's paper in 1925, he proposed actually that maybe relativistic electrons can be seeded in thunderclouds to give lightning. And these authors here in 1999 said, we think that the cosmic ray air showers are the things that are giving us the relativistic electron trails that then, because the thunderstorms have a strong enough electric field, can initiate lightning in the first place, right? And so this means that the cosmic rays are the spark, right? But the fuel is the thunderstorm. It can sustain the fire, but the cosmic ray air showers would be the spark. So we have to go back to what this cosmic ray air shower looks like, where the particles that are created have such enough energy and produce many other particles to create a trail of relativistic electrons and positrons. So you remember when I talked about the energy of different primary particles, such as the cosmic ray of petaelectron volts, it can produce millions of particles, right, at lower energy. And each generation has half the energy of the particle that it came from, right? So you get more particles, lower energy, but you started with so much energy in that petaelectron volt scale. And so what happens with a cosmic ray air shower is this eventually dies out. Those electrons reach an energy in the shower, and the positrons do too, where they stop, right? Because they lose their energy to the air. In a thunderstorm, the extra thing is the electric field. Whoops. The extra thing is the electric field. And so the electric field being present in a thunderstorm keeps those particles moving at such a high velocity, even though in a cosmic ray air shower without a thunderstorm, you wouldn't be able to do that, right? So this is the idea. And there was actually, okay, so here's the thing. If I was giving this lecture last year, that would be the end. I'd be like, oh, we don't know. But there's a very recent result that has taken the community by storm. Did you like that? Basically, I got some laughs, right? I thought that joke was gonna kill. Anyway, so the thing is, Los Alamos National Lab actually went and deployed 2 stations of radio antennas 11.5 kilometers apart, right? That's about 7 miles. And so the kinds of radio antennas here, right, and this is like tens of megahertz range for those in the front who are interested in radio, and there's 11.5 kilometer separation. And these antenna arrays measure the radio polarization of the air, right? They just listen to the air and measure the radio emission and polarization of the radio waves. And they were able to make a map, a 3D map of what happened to that radio emission and polarization of it during during lightning flashes in a thunderstorm, right? And they actually use interferometry, which is a technique that I'll probably come back to, or at least my colleague Peyton Linton will talk about, and maybe I will too at the end of my lecture series, because we'll talk about radio waves again. And they were able to make the first 3D map of the radio polarization of lightning flashes with this interferometric technique. And so they were able to show, so what you want to see here at the bottom, what I want to draw your attention to at the bottom is they can make a 3D map meaning both in altitude and direction, right? And the color shows you through time what the antennas were measuring. And so you see through time the development of the shower from this black region and green region down to yellow. The shower, the lightning flash that occurred had a radio polarization that they could measure and they could map in 3-dimensional space, right? And so this is the broadband interferometric mapping and polarization. So basically the idea is it's always measuring the radio polarization of what it's looking at, these pairs of antennas. But once there's a lightning flash, it now has that radio measurement before the flash, and therefore can see what happens just before lightning occurs. So this is novel. This is not something that had really ever been done before, where you can measure the radio pulse just before the lightning flash. And so they were able to see noisy signatures of what is positrons and electrons created in the created in the thunderstorm just before the lightning flash. And they were able to calculate that the polarization to produce that kind of map aligns with a cosmic ray air shower and not the actual lightning propagation direction. It's really, really cool stuff. And so the idea here is that you have cosmic ray air shower coming in, producing these electrons and positrons, and as those particles are created, because the thunderstorm has such a strong electric field, it can keep those particles and accelerate them more and keep them at really high speeds, really high energy. That creates more and more particles to join the shower, which also feel that electric field from this thunderstorm. And so you get the runaway, the RREA, the relativistic runaway electron avalanche, right? And so they were able to say that we're pretty confident. It seems like it's going to be, the next few years is going to be a very exciting time in this field, because it seems to be very, very good evidence that cosmic rays initiate the lightning. They create the seed, the spark, to make lightning in the thunderclouds. So just to wrap it up, to bring it back to the rest of the universe, you have something that we don't know creating some of the highest energy particles, something we can't achieve yet here on Earth, and those particles propagate through the universe, interacting in our atmosphere, giving you showers of particles, which if they pass through this thunderstorm feel this strong electric field, right, which seems to be initiating lightning and producing gamma ray flashes that we want to fly planes over top of to measure better. And so that means that these high energy astroparticles are there, but we just have to put on the lens to learn more about them, right, and to learn about the world. Thank you. Next. Next week, I'll talk about